Hansi, for that flattering introduction. I'm audible? Okay, great, thank you. So, yes, I'm going to be talking about machine learning, but we are not going to go into the details of the latest techniques because we'll be covering a lot of the basics, which is what is important. The other thing that you should remember is that you should know these basics, but for most, when you use these techniques, there are very good libraries that are available. So you don't have to really code this in, so don't be afraid of what is going to be talked about, in the sense that you'll not have to code for that part, but you'll simply have to understand how those work, so that when you use the libraries, you should be able to jump directly in and go on and use those. So when we talk about machine learning, there are many different things that one has in mind, and it depends on the data set, what kind of questions you are asking. And so the standard thing that is said about these things, like garbage in, garbage out, that is what happens most of the times. And especially now, when there are many libraries, what happens is that people want to blindly use certain techniques. So they have a data set, they have heard about a technique, they try to apply it, they get answers, and they assume that the answers are right, which did not be the case. So it's very important to understand what kind of techniques you can use depending on what kind of data sets that you have. So this is a good flowchart that indicates to you what you should be using when. So this is where you come in, start. You ask yourself, how many samples do I have? And if you have less than 50 samples, then the answer is you just go and get more data. Don't use any machine learning technique, it's no use, right? And then 50, you can also increase it, actually it should be larger than that. But then you ask yourself if the data are categorical or they are numeric, whether the data are labeled or not. And so many times what most people would do is that you have data that have been taken through observations, but you may not have labels for them. And if you don't have labels for them, then what you would do is that you go into clustering. You do unsupervised work, you do unsupervised machine learning, because you don't know enough about the data. You know that it's likely that there are many different types in them, and you try to get to those. Whereas if you do have labels, then you try to do classification, and these would be categorical labels. So you have something, animal, maybe the skin color or the size or whatever, those can also, of course. So the skin color, a color will be categorical variable, whereas if you are asking about the volume or the weight of animals, then it becomes a continuous variable. And in that case, what you would be looking for is something like regression, where you have a continuous variable and you are trying to ask where it's going to fall. And then because what happens is that when you have got some data set where you can have many different features, not all those features are going to be independent of each other, and the dimensionality prediction becomes very important in that, because suppose you have got computed say 30 different numbers for each whatever you have, then you are essentially dealing with a 30-dimensional space. Normally we deal with 3, 4, 5-dimensional space, so one is not clear as to how the curse of dimensionality works when you go to a higher number. Consider the following: if you have got a square and you say that you restrict yourself to 90% in each time, so if you have another square within your square where each dimension is 90%, and the area, the boundary there is 90% to the third dimension. So if you have a cube inside another cube, there is a fine. You are not 70. You have gone to 28%, 27%. And as that increases, really high dimensional hypercube contains smaller and smaller volume of the total volume that you have. Of dimensionality, so that even if you say that 90% of each dimension is within this, the total volume is really small. So that's no use. So when you go to something like 5, 6, 10 dimensions, then you are really sampling a very small part of whatever you have, even if the confidence that you have is large. So what you need to do is that reduce those number of dimensions to a much smaller, and that becomes really critical. Today we are not going to look at most of these things, but we'll only be looking at classification or supervised classification. And when you look at supervised classifiers, there are many techniques available. Linear regression and learning convolutional neural networks, that is what is being used a lot. But what we'll restrict ourselves today to is just these decision trees and random forests, because they do have a lot of important concepts that are used everywhere. So that's where we'll start with. And before that, we'll want to see the different aspects of training data. So when you're looking at training data, what is it you need to look at? So the nature of input data. Are you dealing with images? Are you dealing with features? That becomes important, how you're going to use them, and the dimensionality that I already mentioned. The other important thing is the number of classes. Are they easily differentiable? If you're given 2 classes, then can you quickly say what is what? And if not, then is there going to be a way which you could use to do that? Balancedness, this becomes very critical for many techniques. If you have got 2 classes and examples of one classes are 1,000,000 and examples of another class are 100, then any blind classifier can classify everything in the first class. Accuracy is going to be really high, because there are only 100 examples that you can get wrong out of 1,000,000. So having a balanced class is very important, and there are many ways to make classes balanced if they are not to begin with, called augmentation. We won't go into that, but that's something that you may want to look up later. And so especially if there are some classes that are overwhelming, that becomes very, very bad. And then bias variance trade-off is something that's very important. We'll get to that. So you can have a large variance versus a large bias. You should try to find the middle ground. These 2 techniques, that's what one looks at. So here are examples. If one is trying to separate between stars and galaxies, you ask yourself, what are the features that you can use? So stars will tend to be more concentrated, whereas galaxies are likely to be fuzzy. Then you can ask about areas, full width at half maximum, and so on. So you learned a little bit about sex factor in an earlier module, and that is what it tries to do when you're looking for stellarity. Then it gives you a certain set of parameters and error flags associated with them, and so on. So that's the kind of thing that you can use. So the features that sex factor will output, those can be fed into another system, a decision tree, which will then separate that easily. So sex factor is already doing a little bit of that, but you can become more classy about that using something like that. So here is a simple decision tree that you see, which uses, say, area, magnitudes, and various. So those branches, those are the ones that you need to make decisions about. How will you divide your data set in order to be able to separate whatever classes you are after? And so what one needs is a good labeled training data set for that. And the way you would start is that have a feature vector. So you've got n features, you put them together. This x here stands for all those numbers, however many features that you have, and xi is simply referring to the ith example, and then yi is the ith label. So you've got a set of numbers and a number. I'm generically calling it number, but it could of course be a category. And then that these are your n training samples, xi, yi, so feature vector and label, feature vector and label, and from 1 to n. And then what you're trying to do is that this x is the space of your features and y is the space of labels. You're trying to find a mapping from x to y. Find how you can go with your set of features to a set of labels. And then there can be multiple possible functions, of course, and you want to find out which function is the better one. There's a term called loss that you define, how incorrect your solution may be, and you can have that quantified so that when you go look at a large number of examples, how many of those you are getting something wrong about, and you try to minimize the total amount of wrongness that you have, and that is how you have loss. So again, it's a mapping, and what you're trying to do is that this is what you're trying to minimize. So if you have many possible functions, then what could happen is that given your data set, you find some number, but you may be stuck in some kind of a wrong area, because it may be that one of the parallel functions, other functions may be the right one. Or if you have very few examples, then your few examples may be working great with whatever function that you have come up with, but maybe that is not the right function, and that is where overlearning can happen. You are lulled into a false satisfaction that you have found a good solution, but you really have not. So that's something that one has to look at. Here are some examples where you can have linear separability. So there is a reason why these are not very well visible. You don't have to know what the labels are, because what we are trying to do in data science is abstract the problem into a few dimensions, and they may not be directly physically interpretable, and we'll come back to that. But what you're trying to do is try to find boundaries here. So here you've got non-vegetarians and vegetarians shown by these different shades, and you're trying to figure out if you can come up with a boundary. In this case, yes, that parallel to the x-axis here. But in this case, you clearly see that no single line is going to separate the two classes that you have. You could do something here and something here, but it will be a combination of multiple things that you need to get into. So for interpretive real-life models, what we need are multiple decision boundaries are needed, because the problems are not very simple. And what you try to do is that try to make them locally linear. Even if they are not completely linear, try to at least make sure that they are locally linear. And so here is a diagram where what we're looking for are quasars of different types, and this is a locus of stars in our galaxy. This is one type of quasar, the somewhat high redshift quasars, and these are type 2 quasars. So clearly what you can see is that there are certain boundaries with your eye you can plot, which will allow you to separate those pieces. But it's your idea to come up with those exact definitions in order to do that. And unfortunately this is not very well seen. I hope it's at least seen to an extent. You've got different attributes here, and you're trying to separate out the different classes through that. And these are the leaf nodes, where as you make decisions based on the various features, you have your input feature vectors percolate and go and end up on different leaf nodes here. So the important questions are, how do you choose these parameters, the observables, and how do you decide on the boundaries where they will be separated? So it is an example where you have got some fruits that you are trying to classify, and very conveniently the boundaries are parallel to your x and y axis, so it's easy to just put these straight lines and be able to separate them easily. But here in this case that we saw, that they are not parallel to the x and y axis, that is fine, but you at least have straight lines that you can use there. And so you can have these straight lines. You could even have some regions where you need to have a circle rather than a bunch of straight lines. So you can do a mapping to a different coordinate system perhaps to make it simpler for you. So all those things you have to keep in mind when you want to apply different decision boundaries as you come up with them. And here is a training sample where what you have got the two types, and you have built this decision tree, and they're percolating through these, and one type is gathering here, another type is gathering here. This is from your training set. And clearly what has likely happened is that you have got too many decisions that are being made, and so they are being tailored for individual types of objects, perhaps, I don't know. And that's why the classification seems great here, 100% so far, right? But when you look at all of them that have gone there and you don't have any wrong answers in your training set, that may be an indication that overlearning has happened. You have trained it too well based on individual types of points that you have. So the real test is having a validation set and a test set. So when you apply that to a test set here, what happens is that you are getting 81 out of 90 correct here and 100 out of 111 correct. So about 90%, which itself is not bad, because in many real life situations that's the kind of reality check that you may have. But if you find training set you have 100% classification, but when you give a test validation set it comes to say 70%, 50%, then it's really, really bad. So that's something that you have to be really wary of. And that is where the overfitting comes in. It becomes a pathology. And what you need to do is that perhaps you're using too many boundaries, or boundaries that distinguish inconsequential differences. So that's when you design things, you keep those in mind, and there are mathematical techniques to get you around those. And so more of these are encountered in deep learning, in random forest, which we'll be briefly seeing now, not the deep learning but the random forest. And so how does one have this model flow, or how does this learning go about? So if you encounter an empty decision tree, then clearly there is an undivided field. So you try to ask yourself, let me find all animals that and you find our training set we don't have any. Then clearly that's not a more than say a billion Kelvin, right? You won't find any. So again, that's not the question that you should be asking. So you should choose an optimal predictor to split and an optimal threshold. So the predictor itself and its threshold. Then you recurse on each node until a stopping condition is met. So having a stopping condition is important, because you don't want each object to go into its own leaf. That is where you can be certain that you have been overtraining things, right? And so you have to ask yourself also questions that if you have categorical variables versus numeric variables, what is it, what kind of issues that you could be meeting? For instance, if you have three colors, red, yellow, blue, whatever, and you are trying to classify between those, the order in which you starting do the divisions can become very important. So if you try to separate the blue ones first, you'll ask different questions than if you're trying to separate the red ones. And how does that affect the situation? That's something that you need to ask. So there are certain splitting criteria that you come across. The feature space should in general grow purer as you do your classifications, or the fitness metric should be differentiable, or no empty region should be created. Again, for the same reason that I mentioned, empty regions are not going to help you really. So there are certain numbers that are defined for this, like there is the classification error, and this gets a bit technical at this point. This is something that you can look up easily, and as I said, you don't have to code for this. It's the libraries that handle this, but that's why you also need to know what it is that it is doing, because when you design your features and where they should be splitting thresholds, this becomes important. So if you've got j number of predictors and there are k different classes that you're looking at, and the total number of examples you have got is n, and this is the threshold that you're trying to come up with, tj, which is a real number, then what you can do is that you can assess the quality of the split by measuring the classification error that comes about. So suppose it's dividing it into R1 and R2, so this is how you can define your error. You're trying to maximize over the different classes. You've got k classes, subtract that from 1, and here the p indicates the proportion of training points in R1 or R2, the number of R's that you have. And by doing this maximization and by subtracting that from 1, that's the error that we're getting. So it'll be simpler by looking at this example. Suppose we have got these number of examples. There are total 19 examples here. You are trying to have a single threshold which separates them into R1 and R2. And suppose these are the numbers, how they get split, right? So clearly, if you look at simply the 0 and 6, that's great, right? All objects have gone into 1, so it seems to be something that's purer. Whereas if you look at 5 and 8, it's not so pure. So when you compute this quantity, 1 minus max of 6 over 6 and 0 over 6, you get a 0 here. And similarly here, you get 5 over 13, because 5 is the lower one there, or 8 is the higher one which you have subtracted from the 1. And so what you then have is that you then try to find the predictor by minimizing this. This is exactly the formula that we had before, where what you're trying to do now is find the total number of objects you had, which is 19, n1 and n2 are what have come from this, and then you try to get the errors from that. And so this is how they are defined. And once you get this, that is the error that you want to try to minimize. There are metrics that are available. For instance, there is the Gini coefficient, which is a slight variation on the error index that we saw, which is defined in this fashion again for the different i's, and the definitions are the same as before. The j number of predictors, n is the number of examples that you have, and k is the number of classes that you have, and then you are again trying to select the jth predictor, etc. So what this does, the main difference here is that you have got a square here. So instead of taking 1 minus the max of something, what you're doing is that you're doing 1 minus sum over k and squared of something. Again, looking at the same example as we have before, 0, 6 and 5, 8, what you're now doing is that 6 by 6 squared plus 0 by 6 squared. Again, because this was pure, even here you are getting a 0 like before. But in this case, what you're getting is 80 over 169 compared to the 5 over 13. So 5 over 13, when you multiply both denominator and numerator by 13, you are going to get 13 times 5 is 65 over 169, and you have got 80 over 169 here. So they are fairly close to each other. There are many such metrics, and different matrices metrics are good for different situations. You should look those up, and because then what those allow you to do is that they allow you to do separations based on what the problem is. And again, for the libraries, you can give these various metrics as just an additional argument as a parameter to your function, and when you call that, it's going to compute that for you and give you the answers with respect to those. So with all these, what is important is to be able to define your stopping condition, how much error you are going to be happy with. For instance, if all you want is purity of one class, you don't care what happens to this class, your criteria are going to be different. Whereas if you want things to be roughly pure, different, and that is what you need to optimize for. So you don't split if all examples are of one class, you don't split if number of examples fall below certain predefined splitting threshold. And again, these seem somewhat vague terms because they depend very much on the specific problem that you are trying to come up with. But those are the questions that you could. Even libraries, for instance, random forest, it will do that. But even when you are using random forest library and run it, it's going to give you an answer. There are some hyperparameters that you need to set at the start. Those you have to, these will become related to those, and while the inards will be taken care of by the libraries, it's going to give you answers based on whatever settings that you have done with those. So for those settings, it's important to understand and keep these in mind. So again, don't split if class distribution is independent of predictors. Don't split unless gain in purity based on some index like Gini is above predefined thresholds. So those thresholds divisions are the ones that are really, really critical. And so what one can also do is that have recursive partitioning. So you can have very loose criteria initially, and once you have partitioned on one criteria, it doesn't mean that that particular criteria, that particular variable is out of question. No, you can come back. For instance, if you are trying to classify variable stars in our galaxy, you have got 8 classes. You do the probabilities, and you will keep on separating all your objects, and they have low probability. It will turn out that even if the first thing that you tried had probability of only say 15%, other probabilities are below that. So you may have, is it really that? And maybe it may be a somewhat confusing case, but it may still belong to the very first question that you have. So keep that in mind. And again, this is a generic example, so don't worry about what you have there. So there are of course many decision trees, right? There is bias versus variance that I mentioned earlier, and overfitting becomes a very common problem very quickly with decision trees. So one of the solutions that is suggested is that you average over sets and randomly subset features. So what you can do is that you can take all the examples, behave on that, and do some kind of averaging on that. So what is the bias versus variance issue, right? This can be defined using these diagrams. So what we want to be is in this area where the bias is low and the variance is low. They don't vary much from each other, and they're very close to the target where we want to be. Whereas here is a case of high bias, so it is off the target but the variance is low. They're all clustered together. And this is high variance, not very far from the target but spread out a lot, and this is the worst, right? You've got high variance as well as the bias is fairly high, so you don't want to be in that area. And that is what we are trying to reduce by going from decision trees to some other techniques which at their heart have decision trees, but then do some variation from using all the examples versus all the features, for instance. So bagging is one example where what you do is that you bootstrap to generate multiple samples and train the tree on each of those, and then aggregate the results of all trees. And using these words together, bootstrap and aggregating, the bagging came in. So it's like a bag, but trees. And then trees are fully expressive, and so what happens is that the variance then gets reduced by getting into something. And then there are things like out of bag error. So if in your bag you have put n examples and there are m examples that you have not used, then those m examples you use on whatever you have trained for and find out the error for those, because those indicate whether the examples that you have used were representative or not. These can, however, become somewhat less interpretable, because now what you're doing is that you're mixing multiple trees, and when you're doing that, you have to be careful. For instance, if there is a parameter which is very expressive, and then to that parameter which is which is very expressive, then you may get an error that's non-representative of that. So that's something that you need to be wary of. So low variance means high fidelity, and the same result will apply for nearby results nearby inputs in that case. So here's an example of bagging where you use different examples and so on. Out of bag error, I already mentioned that, and there is bagging can be improved upon. So what happens is that here you got bagging is again not optimal for the reasons that I already mentioned. Suppose you got b number of identically but not independently distributed variables. So this is the b that we are talking about. Then what happens is that as the b increases, this is going to go to 0, but this term is not going to go to 0 at all. And so just by having bagging, you're not going to be able to improve things at all. So the variance in reduction will be minimal in such a case, but that's not what we want. And that is where then the random forest came in. So we said not only do we use different sets of examples, but what we can also start doing is that we can use subset of the variables that we have. So suppose I've got 100 variables. Rather than use all the variables in my trees, I pick randomly, say 10 variables, and use my examples with just those 10 variables. So that is where the word random comes from. And so these are random trees which give rise to the forest. So you are doing bagging now, but with independent trees. The trees are completely different from each other. And so for each tree, randomly select a set of features and predictors. From the full set at each split, then select the optimal predictor with corresponding optimal threshold. So you are now a subset of features that you're using. And so any features that you may be using, like temperature, color, size of the star, and so on, rather than using all 30, you use only a subset of those. And so then this is where the hyperparameters become important for training. Number of predictors to randomly select at each split. Suppose you've got 100 variables. How many are you going to use at each time? Is it 3 or 30 or 50? That is a hyperparameter then. And to optimize the hyperparameter, many times you have to go through a series of things. There are techniques which will automatically optimize for that, but they're very time consuming. So sometimes you have to use your basic domain knowledge and start with that and use a few numbers that you are comfortable with and compare them to see how they go about. Even the total number of trees. Do you use 10 trees, 100 trees, a million trees? If you use a million, it's going to take much longer. They are going to give you better results. But is that do you want to save your time, or do you want to get a better classification? So it will all depend a little bit on that. Then minimal leaf node size, how many leaf nodes can you get to, becomes important. And using cross validation to choose values, that becomes also very important. That is where you train with, say, 80%, test with 20%, and then you change which 20% you are using for testing. By doing that, you are making sure that for the entire set you are getting a fairly balanced set of numbers there. The dimensional reduction that I mentioned a little bit, that's very critical. So if you've got a large number of variables, you figure out which of those, say, top 5, top 10 are the most important, and you can restrict yourself to that. And even within that, you can do various things like random forests and so on. And then there are a couple of other techniques that you have, like you can use naive Bayes technique. We won't be going into the details of that, but this is another training that you can do for where you have got labeled data set. And Bayesian techniques are, of course, the best ones. That is because they carry probabilities with them everywhere, whereas many of these other techniques, you have to be careful how you carry your probabilities with you. There's an example that I had, but we won't go into that. So let me finish with mentioning what practical problems you can run into when you are using some of these techniques. So for instance, with ZTF, what we have is that you've got images, you take lots and lots of images, and then you do image selection to get difference images, and then there are a large number of parameters that are calculated from the original image, that is a science image, from the reference image, and from the difference image. So the total number of variables that you have are well in excess of 100. And then, as I said before, not all of them are going to be independent, so picking a subset of those becomes an important exercise. But then you let your domain knowledge tell you what is important. So for instance, some of the classification that we are trying to do with the alert is that ask yourself for the magnitude difference between the science image and the reference image. You have that. That is an indicator of what kind of variable it's likely to be. Then another criteria, that information is also carried. So such a factor does if you have a nova in a galaxy, you expect to have a galaxy nearby. Whereas if you have a standalone extragalactic object, then that doesn't. Or then how would you try to figure out if there is an asteroid? So you can ask yourself, if you have longitudinal data, multiple images of the same area, can you spot the movement with those? So those questions again depend on the science goal. and from the large number of variables that you have, you'll pick the variables that you really need from those. So the problem definition becomes the critical thing when you want to do classification. So again, libraries are there, techniques are there, you can directly use them, but defining your data set, that becomes very critical. And then sometimes there are obvious variables, but those you have to make sure that those are not telling you too much, in the sense that how did you find out about those variables? Is there information hidden in that? And we'll see an example of that when we look at the notebook today. And so what is the metadata that we have available? Because sometimes you may have a very good variable set, additional data that may be close to that. How can you use that? Make sure that you are able to use that. And one of the most critical bad things can be label contamination. You're trying to separate between stars and galaxies, but then there are some faint stars which you have called galaxies, and that can be very detrimental to your project. So you need to come back and see what is it that you may be doing wrong, how is it that can be improved, and so on. And of course, you don't need to have 100% accurate labels. Most of these methods, because fine data sets, are able to gloss over a small percentage of it, very large percentage, then of course that's not going to be a good thing. And that's the last slide that I have. So I'll stop here with the basic description of decision trees and random forests. Again, I didn't use it with a notebook, so we'll go on to a notebook and go through some examples as we look at this. If you have any questions, please feel free to ask.